I'd like to give you an introduction to aromaticity. And first of all, what I'd like to talk about are the hydrogenation energies of compounds that have multiple double bonds. So we'll start off with cyclohexene, which has just one double bond, and we hydrogenate it. We get minus 28.6 kilocalories per mole. What that tells us is the amount of energy that we get when we hydrogenate this compound. That tells us we have about 28.6 kilocalories tied up in this double bond. We've got two double bonds. We'd expect about double the energy, and that's about what we get. We're about minus 55, which is about double minus 28.6. A compound with three double bonds, we would have expected three times this amount, about minus 84. But instead what we get is minus 54. The difference there is 30 kilocalories per mole. This compound, benzene, is 30 kilocalories more stable than it has any right to be. What makes it more stable? Why is it more stable than what it should be? Before we get onto that, I have to give you a little bit of background. We have to go back to Organic 1 where we talked about how we draw orbital diagrams, and when we draw something like ethylene, what we came up with were three sp2 hybrids, and we also came up with an p orbital that was not touched by the hybridization. Now these two p orbitals bonded together, and that gave us a pi bond. So between these two carbon atoms here, we've got a pi bond and we've got a sigma bond. Now the pi bond is special because it appears above and below the plane of the sigma bond. So this is a bonding pi bond right here, where we've got the sigma bond in the middle, and then we've got the pi bond that's above and below the plane of the sigma bond. Now one thing we need to know about p orbitals is that they exist in two phases. We have a phase up the top and a phase down the bottom. If these phases match, then that's what we call bonding, and that's a good thing. That's when the p orbitals overlap and we get the pi bond. The other situation we have is when the phases don't match. We call that anti-bonding, and that's bad. And if we were to draw an energy diagram for a pi bond, here's what it looks like. We have two electrons in the pi part of the bond. We don't worry about the sigma part. And the two electrons would go in the bonding part, and we wouldn't have any electrons to have to put in the anti-bonding, so that would be a good thing. Alright, let's take a look at what I mean by bonding and anti-bonding. And we can do that by taking a trip to the Orbitron. So this is, just look up Orbitron in Google and you'll see where I'm at. So this is a pi bond that's bonding. This is two p orbitals, and they are bonding together. You can see their phases match. We have red matching with red, blue matching with blue. So that's good. That's a bonding situation. Let's look at an anti-bonding situation. That's this one here. See, the reds and the blues don't match. So what happens is they don't bond. That's a very high energy situation. That's a situation we don't want to see, and we never want to see electrons in anti-bonding orbitals. Alright, so there you go. That's our pi bond setup right there. Anti-bonding bad, bonding good. So this is a nicer diagram of a p orbital setup. This would just be for ethylene, just a double bond here. But if you have benzene where you've got three double bonds in a ring, that's what you've got, is three sets of p orbital pairs, which is a total of 6 p orbitals, all in a circle. Now because they're all in a circle, what we can end up with is what's called pi overlap. So instead of the electrons being stuck in between these p orbital pairs, they actually get delocalized and can be all around the ring. So we don't really have three double bonds in here. What we have are just a multitude of partial bonds all around this ring. So what we're looking at is not a situation where we've got three double bonds here, but we have a situation called resonance. So this is what we're talking about with resonance. These two things here are resonance structures. These represent the extremes of benzene, where the double bonds would be located if it existed in this way. But it doesn't exist in either of these forms. It exists in a form that's in between these two, where the electrons are all around the ring. And this is all due to what I was talking about before with the p orbitals all being in the same phase or being overlapped and having a very nice situation. And this is where the stability of benzene comes from. That extra 30 kilocalories I talked about earlier is due to the fact that electrons are not stuck in these double bonds. They're resonating and they can be anywhere in this ring. And as you can see here in this diagram, the electrons will appear above and below the plane of the sigma bonds in the benzene ring. So it's a very special situation that we're seeing with benzene right here. What I'd like to do now is take the information we've learned about p orbitals and then put them together into an energy diagram for benzene. Now here's what we know. We know that orbitals, p orbitals that are all overlapping with the correct phases, all in phase, all overlapping, is the best situation we could possibly have. And with benzene, that means, in this instance, having all the pluses, or in this case all the blues up top and all the oranges down the bottom. And that would create the lowest energy possible situation that we could have for benzene. But as you can see, we can flip some of these p orbitals and we can make different energy situations. We know that this is the best energy situation. What would be the worst? Well, the worst situation would be to have all the p orbitals alternating. We have the orange up here, blue, orange, blue, orange, blue, orange, all the way around. That would be the worst situation. So that represents the worst energy that we can have. Now we've got some other possibilities where we're flipping p orbitals as well, and these combinations happen to be of equal energy. This one and this one happen to be of equal energy for the benzene system, as are this one and this one. Now this one down here has more overlap than this one does, so this one is of lower energy than this combination is. Same with this one. It has pretty much the same number of overlaps, so it's got about the same energy, and this one's worse, so it's got higher energy. And again, these have about the same number of overlaps as well. So we've got all overlaps going here, we've got no overlaps going here, and we've got some overlap here, less overlap here, and less overlap here. So what's that mean for the energy diagram that we're seeing with a benzene ring? Well, here we go. We've got a benzene ring. This is what the energy diagram for the pi electrons is going to look like. We've got the lowest energy situation here, and then we've got the highest energy up here, and then we've got these other intermediate situations down here. Now, as we know, when we're filling an energy diagram, what we always do, we always start at the bottom and we move our way towards the top. Now, since we're only dealing with the pi electrons here, we know that each of these double bonds contains 2 pi electrons. That's for a total of 6 pi electrons. So the energy diagram for benzene is going to look like this. Now there's a line here that we can draw in between, and this represents the bonding, and this represents the anti-bonding orbitals up here. Now remember, the bonding orbitals are good and the anti-bonding are bad, and since every electron we've ended up with is paired and happens to be in the bonding section, then we know that this is going to be a favorable situation for these pi electrons to be in. I'd now like to introduce you to a compound called Cyclo Butadiene. This is different to benzene. Whereas benzene had 6 different possibilities, we only have 4 possibilities of the way we can arrange our p orbitals. Now what we'll notice is, first of all, we're going to get 4 energy levels. We usually get one energy level, one set of energy levels for each carbon in the compound. That seems to be the way it goes. And that's generally because there's 4 pi orbitals to consider. Now it turns out that if we'll get our lowest one by doing all the p orbitals the same. So having the p orbitals all black up the top, that's going to be the best and lowest possible energy situation we can have for an energy level. The worst situation is when they alternate, when we go black, white, black, white. So that's the worst. Now these two are actually of equal energy. So we have 2 blacks over here and then 2 blacks down the bottom here, And here we have a black here and a black here and a white here. And these are actually of equal energy, so we end up getting two of these at the same energy level. So now we've got, remember we've got energy going on up here. Actually, put it over the other side. And what we've got is, we've got 2 pi electrons in this double bond, we've got 2 pi electrons in this double bond for a total of 4. Now I'm going to put the electrons in. I'll put 1 in here, 1 in here, that's 2. And because these are the same energy, I have to put 1 in here and 1 in here. I can't put both of them in the same energy level. So what I've got in essence is a situation where I've got 2 unpaired electrons. So because of the arrangement here, this is forced into a situation where we actually have 2 unpaired electrons. And in reality, what this compound looks like is this. This paired electron would be for the double bond that's actually bonded, and these 2 unpaired electrons are actually on separate carbons, and they cannot bond. They can't bond because the energy diagram won't let them. Now I want you to keep in mind this only happens because this compound is flat and is forced into this particular situation. So this compound is incredibly unstable, and it is called anti-aromatic. Now this is in contrast to benzene, which is called aromatic. And we noticed that that was going to be a very stable type situation.
I'd like to introduce you to Cyclooctatetraene, which is of similar type to benzene and Cyclo Butadiene, which we already looked at. Cyclo Butadiene had 4 pi electrons, benzene had 6, and this one has
8 electrons. Here's the energy levels right here, and we get that based on the ring, which is an 8-membered ring, so we're going to have these 8 energy levels. And we're going to have certain ones that are equal, and ones that are the worst, and ones that are the best down here. Now when I've got 8 electrons to deal with, I put them in. I'll do 1, 2, 3, and go over here, that's 4, 5, 6, 7, and 8. And again, I'm left with a situation where, because this is flat, these 2 electrons are left unpaired. So what this really looks like, if it is flat, it looks like this. And one of these double bonds is actually not bonded to each other. We've got 2 unpaired electrons, which makes it incredibly unstable. So this system actually does not exist. And what will happen is that this ring will actually go out of the plane and turn into something more like a lawn chair shape. And the reason it does this is because it is now no longer flat. All of these energy diagrams we've been talking about up to this point all assume that the system remains completely flat. That's how we get all these equal energy levels. Now, with the double bonds not remaining, with the p orbitals all being able to overlap, now this is not subject to those kinds of rules. And this will not be considered to be aromatic, nor would it be considered to be anti-aromatic. It's just considered to be non-aromatic. And this will allow us now to figure out what kind of rules we can have for aromatic, anti-aromatic, and non-aromatic systems. And I will summarize those right now. Alright, so here's our summary of when we're going to get aromaticity, which is going to be a good situation, and when we're going to get anti-aromaticity, which is a bad situation. And then what we're going to say is anything that doesn't meet either of these 2 sets of conditions here is going to be considered non-aromatic and won't be subject to either of these rules. So here's what we've learnt so far. In order to be aromatic, the following conditions must be met. First of all, the system must be cyclic. So that was like with benzene, that was a cyclic system. And all the ones we've talked about so far have been cyclic systems. All the double bonds must be conjugated. That means they must be alternating. They must be single, double, single, double, single, double. And all the ones we talked about were like that. Thirdly, the system must be flat or planar. And we needed that so that all the p orbitals overlapped. And lastly, for aromaticity, we must have 4n plus 2 pi electrons in the system, where n is any integer. And a lot of people get confused. Say, well, what's n? How do we have to figure out n? Well, n is just any integer that we want to make, and it could be 1, 2, 3, 4, 5, whatever. If n is 1, then that means we're talking about 6 electrons. That's what benzene is. So benzene was aromatic. 10 electrons, 14 electrons, all of those are fine for aromatic systems. And you'll notice they all fit the equation 4n plus 2. So 4 times 2 plus 2 is 10. 4 times 3 plus 2 is 14. 4 times 4 plus 2 is 18. So you can see the progression. 6, 10, 14, the next one to be 18, 22, etc., etc. Now, to be anti-aromatic, the following conditions must be met. It's the same conditions. The system must be cyclic. The double bonds or charges must be conjugated. It must be alternating, single, double, single, double. The system must be flat, and there must be 4n electrons in the system, 4n pi electrons in the system. So numbers like 4, 8, and 12 are going to be anti-aromatic systems. And like I said before, everything else is considered to be non-aromatic. So let's take a look at some examples of those and just try and summarize what we've learnt from this introduction. Now what we learnt was that with benzene, our energy level diagram looked like this. And we had 6 pi electrons, 2, 4, 6, and we put the electrons in our energy diagram like this: 1, 2, 3, 4, 5, and 6. And we end up with a nice system where all the electrons are paired, they're of equal energy, and that's what gives us its extra energy, or its stabilization. And you'll notice again that the rings, it's a ring system, and that the double bonds are all conjugated. It goes single, double, double, single, double, single, double, single, all the way around. So this one is going to be aromatic. So all the conditions fit for that. And just to clarify what I mean by flat or planar in this instance, when I draw the p orbitals in, you'll see that they all overlap. And it's because the ring is completely flat. It's not like it's bent anywhere. All those p orbitals have the occasion to overlap each other. Now, if you'll remember, for the Cyclo Butadiene, that was the 4-membered ring system, the energy diagram looked like this. And we have 4 pi electrons to deal with. And again, we're dealing with a system that's cyclic, we're dealing with a system that's conjugated, double, single, all the way around. And we've got 4 pi electrons we need to put in here. We put 1 in here, 1 in here, 1 in here, and 1 in here. So we end up with a situation where the 2 electrons are unpaired, and that is anti-aromatic. And of course, we're assuming that this system remains flat and that we keep complete overlap between those p orbitals. So it's going to be anti-aromatic right there, and that's a very bad situation. That compound actually doesn't exist because it would lead to, it doesn't exist in this form anyway, because it would lead to this kind of situation where we have the 2 unpaired electrons. So what it will do, in order to avoid this, it will sort of twist out of the plane, and when it twists, it allows for those double bonds to reform. Except since this is a four-membered ring, that twisting is very limited, so the ability for it to actually bond with these two electrons is very limited here. So this is considered to be non-aromatic once it's not flat. Once it sort of bends out of the plane, it's non-aromatic. Right, the other one we talked about was the Cyclooctatetraene. That was the one with the 4 double bonds in the 8-membered ring system. Look like this, look like a big stop sign. This one here. And when we drew the energy level diagram for that, we got something that looked like this. And we've got 8 pi electrons in here. And we stick them in. We've got 1, 2, 3, 4, 5, 6, 7, 8. So now we've got those 2 unpaired electrons again, those pesky unpaired electrons. So we know that this is anti-aromatic. And which is very bad. And what this will do in order to avoid being anti-aromatic is it will stop being flat. So it will become that lawn chair shape that I described earlier. So all of those double bonds can now bond together, and we're no longer subject to the rule of the anti-aromatic system. We don't have to have these unpaired electrons hanging around here. But that only happens if we consider the system to be flat. As soon as we make it something that's not flat, we don't have to worry about the p orbitals overlapping, so we end up getting a situation that looks like this. So in summary, here's what we know. We know that 4 pi electrons and 8 pi electrons are bad. Those fit the 4n pi electron mold, and we know that that's a bad situation, and 4n pi electrons lead to anti-aromatic systems. But again, it has to be completely flat if we're going to talk about that. Completely flat, planar, and conjugated. And going back to this one, the 6 pi electrons, so 6, 10, and 14 will all lead to 6, 10, 14 pi electrons. Those are all 4n plus 2 pi electrons. And that leads to aromatic systems. And our aromatic systems are very favorable. So we like that.